Well, CFD behind the scenes, and I'll leave it to each of you individually to decide what the C stands for. You can take this either way that you like. But whichever way you take it, you can't deny it, there's a lot of it about. In every seminar that we have that touches on aerodynamics at all, you're going to see a picture looking like this, or maybe bigger and brighter than this, but several of them. And it will be explained to you how essential that was to the project that's being discussed. But of course, it's not only in aeronautics that CFD has become important. Very much used in the automobile industry, particularly racing cars. And in fact, in almost every situation where fluid flow is important, many sports, and even in areas which you might not think really call for scientific study at all. I don't know. I mean, so we have the impression from all the seminars that this is an enormous value for people who design airplanes. But sometimes we also have a feeling that it's just a branch of the entertainment industry. In fact, it's a little bit like this. It's full of noise, it's full of colour, it's spectacular, it's intended to blow your mind away, it's intended to disarm criticism. And the skeptical point of view is put very well by our seminar speaker of 2 weeks ago, Doug McLean. And this is a quote from his really excellent book, Understanding Aerodynamics. He says, these days, it is common to see a complicated flow field, predicted with all the right general features, and displayed in glorious detail that looks like the real thing. Results viewed in this way take on an air of authority out of proportion to their accuracy. Well said. And what I'm aiming to do is something in the nature of a backstage tour. You know, when you see something like this, you realize, of course, there are a great many people behind the scenes who have been sewing costumes and who have been building sets and have been operating the lights and setting up the sound systems. And if you're interested in the theatre, it would be a really nice thing if you get somebody to give you a backstage tour. You have to know the right person. Well, okay, you do know the right person, and I'm going to give you a backstage tour of CFD and see whether that changes anything. So you've all seen this picture many times. And Moore's law is something that has a number of formulations, but roughly speaking, it says that everything that is impressive about computers will double every 18 months. And what's plotted here as a measure of importance is MIPS, which is millions of instructions per second. How many MIPS will $1,000 buy you? So starting way down and going up and then taking off into the unknown future. It's a fairly convincing straight line on a log plot. And it occurred to me to plot my own career in CFD in relationship to this. This is the part of my career which I've been involved in CFD. And so you take this along the x-axis and you see what that corresponds to along the y-axis. And it corresponds to a gain of roughly 10 to the 8. And that's an awe-inspiring thought. I'd never realized that my own life would ever contain a number like 10 to the 8. It just doesn't seem reasonable. And in fact, it's more than that, because the axis is what would $1,000 get you? Well, people are spending much more on CFD than they used to. They're spending much more on individual runs. So that factor of 10 to the 8 ought to be probably 10 to the 10, 10 to the 11. So somewhere way up there in the astronomical range. But you know, every journey of 1,000 miles starts with a single step. So it's interesting to go right back to the beginning, before there were computers, and look at some of the history of the subject. And the guy who, in my mind, really started it all was this guy. So he was a British mathematician. He had a distinguished career. He was very, very inventive. He had lots of original ideas. But his first job, his first employer was a hydraulic engineer, firm of hydraulic engineers. They asked him, they had a project that drained the water from a marsh. And his job was to plan how to dig the ditches in the most efficient way to remove the right amount of water. And this was a very messy problem. And he realized as a mathematician that none of the tools he had in his kit bag were really going to be very effective on it. So he came up with a numerical method. And it worked. And his employer was very pleased, and he was very pleased himself. He thought, maybe we can do more with this idea. And the next project that he went on to do was to compute the stresses in a masonry dam. And this was important at the time because there had recently been a big dam failure in Egypt. A masonry dam had collapsed. There had been lots of loss of life and property. And it was because people didn't know how to calculate the stresses in something as complicated a shape as a dam. If dams were nice rectangles, they might have managed it, but they're not. And this project was much larger than his first project, and it required the efforts of a team. So he built a team, and apparently he recruited small boys who were good at arithmetic, and gave them these calculations to do, and every time they did 10 calculations that worked out correctly, he gave them a penny. So this is how we're able to place his efforts on that chart of cost against time. And the boys were called computers with an O, someone who computes. Now, people have done calculations by hand, of course, for many years. All the great mathematicians of all time were interested in getting numerical results. But this was the first time that it had been done by mass production. So none of these small boys knew that they were computing the stresses in a dam. They were just doing the arithmetic they'd been told to do. And so, in a sense, this very much was a computer. We have elements that are programmed, which, when you put them together, produce some result which is very much larger than the parts. So, after that, he got very ambitious. He started thinking about weather forecasting. And his ambitions were more than doubling every 18 months. Because really he was a meteorologist by profession. He understood the equations that govern the weather, the equations that people still use today, more or less, to produce numerical weather forecasts. And he figured out a numerical way to solve these. And but this got interrupted by the coming of the First World War. And Richardson himself was a pacifist. And the deal was in those days that if you had a conscientious objection to serving in the military, you could be exempted, provided you volunteered for something. And he volunteered to drive an ambulance, which is a pretty hazardous thing to do. It takes you out behind the lines. And although people are not supposed to shoot at ambulances, they sometimes do. And he spent his evenings, wherever he was living, trying to do this calculation by hand, usually by the light of a candle. He got a long way through it, and then in some upheaval, all his notes got lost. They turned up a few weeks later in a coal cellar. He ploughed through all of that. And what he was trying to do was he was trying to solve partial differential equations. So partial differential equations are the natural mathematical language in which to talk about fluid mechanics. And here we have the Navier-Stokes equations for compressible, viscous, three-dimensional, whatever, flow. And it's fairly intimidating. And so what are you going to do about that? Well, his idea had to do with finite differences, and I'm going to explain the idea behind finite differences for the benefit of any of you who've not come across it, but I'm pretty sure this is not going to be news to many of you. You create a grid, and you put numbers at the points on each grid as a way of representing the solution that you hope to compute. And you're going to have to differentiate this solution to find out whether it satisfies the partial differential equation. So whenever you want to evaluate a first derivative, you look at the number here and the number here, and you subtract them, and you divide by twice h, where h is the size of the mesh. And if you want a second derivative, you take these three numbers and you apply these weights to them. And if you want the Laplacian operator, you take a star of 4 points, and you apply some weights to that. So what he basically did was he looked at every term in his governing equations, replaced them by finite differences, and then aimed to solve the problem by arithmetic. It's quite a striking thought in itself that arithmetic might prove more powerful than calculus. But it's actually true. And he realized that the mathematics of his day had got into a bit of a blind alley. If you were going to talk about shapes that were very complex, governing equations that were nonlinear, the equations of state that were strange, not a perfect gas. And he wrote a book, in fact, called Weather Forecasting by Numerical Process. And he did these trial calculations during his service. And what he had available was some detailed atmospheric data over a certain region of Germany that had been collected a few years ago in great detail. And he worked on these, and the outcome must have been a huge disappointment to him, because his weather forecast predicted by the end of that day there would have been winds of 100 miles an hour. And in fact, it was a perfectly normal, ordinary day when nothing really happened. And he'd actually made no errors in his physics. The equations were correct. He'd made no errors in his mathematics. He'd made the right deductions from them. He'd made no errors in his arithmetic. People actually checked later. Something still went wrong. And it was unexpected. It was something that Richardson would have certainly found out for himself if he'd done enough of the same calculation. He would have observed a pattern. But he had limited data to go on. And in my CFD class, I illustrate this by solving a much simpler equation. I illustrate this by solving the equation that governs the one-dimensional flow of heat. So the rate at which temperature changes with time is some constant times the second derivative of temperature with respect to x. That governs all sorts of diffusion problems. There are many diffusion problems that are part of weather forecasting. And so you set up your grid, and it's now in x, and it's now in t. And you consider replacing these things by finite differences. There are many ways in which you can do this. Two of the most obvious would be that you use the time derivative from these points, space derivative from these 3 points, and that actually doesn't work. And it doesn't work for a reason which is not particularly mathematical, it's physical. Because heat conduction is not a reversible process. Heat conduction forward in time and backward in time are two different things. Heat conduction backward in time is unstable. But this stencil is symmetrical. This stencil makes no distinction between the past and the future. So without actually doing any algebra, you might have become a bit suspicious of that. This one, on the other hand, goes in one direction, only in time. That here is what is happening at the present. We use that to predict the future. That's in accordance with the physics. It's perfectly okay, and it works. Well, after that, a lot of people tried using numerical processes to do a lot of things. And some of the early ones were quite impressive. But I only want to touch on the ones that were really decisive in shaping CFD. And undoubtedly one of these was the atom bomb project in Los Alamos. And the way you make an atom bomb is you have a conventional high explosive which compresses the uranium to beyond critical density, and then it goes off. Take my word for this, don't try it at home. Because this isn't the sort of thing you would want to mess about with by trial and error. You'd really much prefer to have some nice, safe pencil and paper way of making these predictions before you actually make the darn thing. And so they assembled a team of computers. These computers were a bit older. They were high school kids who were good at math and who'd been granted deferment of their military service. And they were given to the famous physicist Richard Feynman to organize. And you can find out some more detail about that in one of his memoirs, which is very well worth reading. And it wasn't simply some paper. They had IBM adding machines. They had things with like a typewriter keyboard that you could type numbers in, and two numbers would get added or multiplied or divided. And it was a few years before they were able to take square roots, but that was the computing technology of the day. One interesting thing is that these kids were smart, and they did know what was going on. And they began making suggestions, like, why don't we do it like this? And so this was actually a self-programming computer, which is a luxury that many of us really like to have. But one major issue arose because of the presence of shock waves in any kind of explosion. And shock waves, again, are irreversible physical processes. They need taking special care of. The cure for this was, or the way of analysing this, your way of realising mathematically what was going on, was due to John von Neumann, who at that time was a kind of general troubleshooter for the American scientific war effort. He went around wherever people were having problems, he fixed their problems for them. And he found a way to analyse the stability, which is nowadays called von Neumann analysis. And he also, in connection with Robert Richtmeier, came up with a way to stabilise the shock waves. They were not really calculating the shock waves as they should have done, as discontinuities. They were calculating them as regions of smeared out high gradient. But this went very well. And von Neumann was extremely impressed, and he was a very influential guy. And he wrote a report for the US government in which he said, look, this is the wave of the future. This is how scientific applications of mathematics are going to go. He even said this will completely change the way we think about mathematics. It will change what we think of as being elegant, what we think of as being simple. It's simple if the machine can do it. No matter how many operations it actually takes, it's simple if you can tell the machine by a set of simple instructions. So he got the idea of weather forecasting again. He revived Richardson's dream. And there was a team at Princeton Institute for Advanced Study. They had built an actual computer there called ENIAC. It was a real computer. And he programmed some of this stuff that Richardson had thought about. And their first test was to see if they could do a one-day forecast for the local weather in the Princeton region. And it turned out they could, except it took 24 hours to run. So, but you've seen the future. You're kind of thinking something like Moore's law is going to come along. So I'm just filling in some points along this trajectory. Now, CFD didn't really make very much of an impact in aerodynamics until the late 60s and the 70s. And the big stimulus for this was the battle for the transatlantic passenger market. And we were just starting to get jetliners that could go non-stop across the Atlantic. And suddenly it turned out there were a lot of people who actually wanted to cross the Atlantic who were prepared to pay good money for it. So at the same time, Boeing and Airbus were developing designs for airliners. And these were going to be aircraft that flew relatively close to the speed of sound. They were going to be traveling at maybe Mach 0.7, 0.8. whereas the aircraft of World War II had only travelled at something like Mach 0.5. And people were forced to realise they did not understand transonic aerodynamics. Very little experience with it. It was a very messy, mathematical, non-linear problem. None of the tools that people had available were going to work. Very difficult to do experiments at transonic speeds because the characteristic of transonic speeds is that they simply spread out sideways. And when they spread out sideways, they encounter the wall of the wind tunnel and you get interference. So what you're going to do? Well, numerics is the resort. And what you want to understand is the so-called transonic drag rise. If you plot the drag of an airplane, or just its wing, as a function of Mach number, you see it is relatively stable up to a Mach number of about 0.8, and then it starts to increase, and then it increases very rapidly. It reaches a maximum somewhere around Mach 1. And so where are you going to fly on here? Well, if you're going to fly down here, you'll be very efficient, but you'll be very slow. And people would prefer to fly with your competitor, and that will going to get you there faster. If you fly up there, you'll get him there fast, but it will cost him a lot. You'll have to charge him for all that extra fuel. So you want to fly somewhere around the point where the curve begins to bend upwards. And so you would like to ensure that upward bend takes place as late as possible on that diagram. So that's the objective. And then people thought, well, there are going to be two ways of doing this. All of the theoretical effort up to that time had been based on the potential equation. The potential equation, you define a single variable from which you can deduce the density, the pressure, all the velocity components. It's a scalar equation. There's only one unknown. Or you could try the Euler equations, which are direct statements of the conservation laws for mass, momentum, and energy. They have 5 unknowns. And they also didn't look very much like any equations that people had solved previously. So there was a natural prejudice in favour of the potential flow equation. Now, you know that it can't quite work because the potential flow equation neglects changes of entropy, and entropy changes across a shock wave. But it changes very slightly if the shock wave is weak. And if you're aiming for efficient flight, then you're going to be doing your best to make sure gains in entropy are small. So one would assume, in the beginning, they will be small. And the way that comes out is that you can't get every aspect of the shock jump perfectly right. You're going to have to make a choice between getting this perfectly right and making a small error in that, or the other way around. So the German Applied Mathematical Society had begun to organise some biannual CFD contests starting in 1975. And they said, well, we're going to organise a workshop. It was in 1979. And we're going to invite all the people from all over the world who are trying to write transonic codes to come and submit their solutions to some standard test cases that we will devise. Actually, this was quite remarkable, considering the fact this whole activity was driven by commercial rivalry, that people would, in fact, be willing to get together in one place and talk about the science of it. But in fact, they were. And the agreed test cases was transonic flow over two-dimensional airfoils. So back in those days, there was not nearly enough computer capacity to consider the full three-dimensional geometry, but you consider a two-dimensional slice through the wing, and you try to find an efficient airfoil section as a beginning. And the scatter in the results was just incredible. Nobody who went to that workshop was prepared to see that the results were all over the shop. These are pressure distributions. Admittedly, this was one of the most severe of the cases. The results for other cases were not quite as bad as this, but this really dramatized things. You solved by the potential flow equation by something that people called fully conservative. It conserved mass. And you got these pressure distributions that were way off. If you were non-conservative, you did not conserve mass, they were even worse. If you solved the Euler equations, things were starting to look as though they might work. There was much more of a consensus among the people who were solving the Euler equations. But methods of solving the Euler equations were in their infancy, and they were very slow. Here's another way of presenting the results. The horizontal plot is just 1, 2, 3, 4, 5, up to 15 different authors. Vertically, we're plotting the predicted drag coefficient. And the group of fully conservative methods, partially conservative methods, a lot of scatter. The Euler equations, distinctly less scatter. Same thing true for lift. And if you're wondering what those yellow stars are doing there, that's the one that I had something to do with. And we were pretty good. We were in amongst the consensus of the best methods. And I think it's quite possible that for a few months we had the world's most accurate Euler code. It soon turned out we also had the world's most expensive Euler code. And that, of course, was the difficulty that people were left in. The potential theory, it seemed more or less hopeless. It's not that people really completely stopped using them because that was all they had, but after this, people certainly stopped trying to develop new potential codes. All of the effort started to go into solving the Euler equations, but these seemed to be very expensive, and there was some speculation at the time that they were necessarily very expensive. They had some mathematical property that you couldn't help but be expensive when you invented a method for the Euler equations. I'd just like to explain where the difficulty comes from. And it's an example of a difficulty that will recur. Shock waves often occur as a result of some geometrical feature. So a surface takes a sudden bend, and for the flow to follow it, it has to go through a shock wave. And the shock wave has no option but to live at that corner. Well, here's a shock wave, and it terminates a region of supersonic flow. The flow comes in subsonic, accelerates to supersonic, shocks down to subsonic again. And there is a shock wave, but there's nothing to hold that shock wave in any particular position. It's sitting on a smooth surface. What is going to hold it there is going to be some incredibly delicate balance of forces. It could have sat lots of other places. In fact, if you do the viscous calculation and introduce a boundary there, that does very much affect where the shock wave sits. And so to get this delicate balance right, everything has got to be perfect. You can't afford to have any approximations, even approximations that you believe are very good and rather harmless. So this is an image of that same flow from a modern computation. But like I say, people didn't really completely stop using the potential flow equations because even inaccurate CFD can be useful. And in fact, using really very inaccurate CFD, the drag of the Airbus 310 was reduced by 30% compared with the drag of the A300. And several reasons for this. One is that CFD gives you a lot of detail whether you want it or not. It's up to you to think of what you're going to do with it. And you might not be wise to rely on the prediction of the actual drag, but it might be quite okay to rely on it for trends. To say, well, if I tweak the shape a bit here, what happens? What direction do things go in? And provided you're backing things up with a lot of experimental backing. If you ask the Airbus people what the real benefit had been, well, one benefit was enormously reduced design time. That they reckoned they designed in a year a wing that would normally take them 3 years to design. But even more than that, they said, it encourages you to be adventurous. If you have some crazy idea, you're going to feel really stupid getting a wind tunnel model made and cutting metal and putting in the tunnel and discovering it's all wrong. Whereas if you have a really crazy idea and you test it out in your CFD code, probably nobody else ever even knows that you did it. So the envelope kind of expands. And as we'll see, these are examples of how CFD is much more than a replacement for experiments. So people were talking of CFD at that time largely as a replacement for experiments. There was a standard joke going around about how it might eventually be replaced by the wind tunnel. But a replacement for experiments was certainly what people thought they were doing in the early days. And just so things have got a lot better. So we can put a few more data points on the timeline. Put the Stockholm conference on there. But people were now really interested in solving the Euler equations. And from this point onwards, a method became very standard in CFD. It's called the finite volume method. Because when the geometry you're dealing with is fairly straightforward, you can maybe describe it by building a rectangular grid or a grid that's almost rectangular. When you have to deal with the shape of an airfoil, your grid tends to become curved and try to follow the surfaces. And it's very hard to think how, on a curved grid, you would come up with a finite difference form to find that derivative there. So the big lesson was don't try to differentiate, only integrate. Because the conservation laws are basically integral laws. And so when we're going to divide the space up into a lot of little boxes, in principle they can be any shape at all, and each box will contain a certain amount of mass, momentum, and energy. And then some of that stuff is going to flow from one box to the next. It's technically called a flux. And if you can calculate that flux, and you can make sure that whatever mass is lost by this box is gained by its neighbour, then nothing ever gets lost. You're conserving stuff in exactly the way that nature should. And this works even when the flows contain shock waves. An argument against using finite differences when there are shock waves, for instance, a shock wave is a discontinuity. There are no derivatives there. Trying to imitate them sounds like a bad idea. But you can always do integrals, however complicated the flow looks. So the decisive shift from finite difference methods to finite volume methods took place at about this time. And the boxes look something like this. So this is a typical grid of the time, more or less drawn by hand, maybe a few formulas cooked up to describe the shape of these curves, but some set of coordinates that are wrapped smoothly around the airfoil shape. And it seemed that you should have more detail in the mesh in certain places, but that was just based on past experience. It was based on the experience of the user to come up with a good grid. Some users were better than others at inventing grids to use for their CFD code. Well, so a small technical interlude. There's a general expression that gives you the error to be expected from a CFD code. And it takes the form of some constant, which depends on the particular method you're using and the geometry of the grid. It depends on h, which is the measure of the grid spacing. It's not necessarily the size of any particular cell, it's a representative size of the cells in general, raised to the power p. And on dimensional grounds, the other factor in here has to be the pth derivative of the thing you're trying to calculate. And p is usually an integer, and it's called the order of accuracy of the method, and it has a big influence on efficiency, because if I divide h by 2, and p is 1, then I simply halve I double the accuracy. But if p is 2, and I make h half as big, the errors are reduced by 4. P is 3, they're reduced by 8. So a large p sounds like a good thing to do. but it's expensive. You get more and more and more terms coming into the finite difference expressions. And there's another snag as well, which people are going to realize about this time. And it's a mathematical barrier first pointed out by this guy, Sergei Godunov, another mathematician, famous for some deep contributions to linear algebra. But apparently, the institute he worked for acquired a computer earlier than they thought the system was going to give them one. And they said, look, we need a program to run. You go and write a program for us. And he wrote a program, he started to get interested in scientific computing. And for any p that's greater than 1, he showed that when the flow contains shock waves, it will also contain oscillations. It's like the Gibbs phenomenon from Fourier analysis. And it was published in a rather obscure mathematical journal in Russia. Not very many people in the West knew all that much about it. There were still people who were trying very hard to get second-order codes that would not oscillate, and they couldn't understand why it would never work. And it was a very, very valuable service that mathematicians can sometimes perform, is say, well, don't bother doing that, it's not possible. And Godunov was awarded an honorary degree by University of Michigan. Professor Van Leer was the guiding spirit behind that. And this is a group photograph taken on the Wayfield. And in fact, really all the great and the good of computational fluid dynamics were present at that meeting. You can see Sergei Godunov on the top of the mound. You can see Professor Van Leer looking very pleased with himself, as he should. You can see the FXB building in the background looking very new and clean. There's a lot of trees along those walls now. So trees have come and hair has gone. It turned out this barrier was not the absolute barrier that it seemed to be. And it only applies if you try and solve linear problems by linear methods. And the way around it is to introduce some nonlinear feedback. And again, Professor Van Leer was very influential in devising ways of doing that. He wrote a famous paper. It was spread over 5 parts. And this idea of feedback between the solution and the algorithm is still a very central element. I went looking on the internet for pictures of Godunov, and to my surprise came up with one of myself. And this happened at a conference in France. He'd just made some rather strong criticism of a paper that I'd presented, and this was taken after the paper. And I am defending myself, and I'm trying to defend myself speaking French because he doesn't speak very much English. But the idea of basing his idea was to base the way that information flowed from one box to another in the way that waves would actually flow naturally, acoustic waves, from one box to the other. Again, that's a standard part of CFD. Okay. Shock tube is a familiar idea to aero students. A tube with high pressure one side, low pressure on the other side. You break the membrane that separates them. High pressure air rushes into the low pressure air. And in an XC diagram, you see a shock wave going into the low pressure gas, followed by a contact, which separates the gas that was on the left from the gas that was on the right. And another very influential paper, in that so much as it pointed out a problem rather than cured a problem, came into the Journal of Computational Physics in 1978. An author was Gary Sod. These are all attempts by various methods to predict the flow in a shock tube. This one, which is Godunov's method, is kind of halfway decent. Most of the others have serious flaws. Either there are strange oscillations or things are badly smeared out. And some more At the time, the opinion was that this was a really, really hard problem. It was the problem which is the climax of your CFD career, if you could solve this problem well. Nowadays, it's the entry-level problem. If you can't solve this problem well, you're not in the game. But it's still used. So this is from Tim Iman's thesis of a year ago. This is our entry-level calculation. The paper that Chris alluded to had to do with the way in which you actually calculate the flux from one cell to another. And while all this activity was going on, I was actually on the sidelines because not everybody was up for the free exchange of information. And the work that I was doing got classified by the UK government as confidential. I wasn't allowed to go anywhere and talk about it, and I saw all these other people having such fun. Finally, I was released from my cage in 1980, and then this was the paper that I wrote. I'd been waiting to write it for about 4 years. But the paper that really changed computational aerodynamics was this one by Anthony Jameson, at that time from Princeton. And his contribution was to show the Euler equations did not have to be solved slowly. They could be solved quickly. And he did that by modularizing the calculation. One module for differencing in space, one module for differencing in time, one module for this, one module for that. And he got the modules to work together extremely well. And his solutions were almost as fast as those of the potential equation. But we weren't yet into the realm of colourful fluid dynamics. This was how he typically presented his results. So a pressure distribution over an airfoil. And this plot shows how quickly the errors are going down, and they're going down very quickly and very steadily. This was the thing that really caught people's attention. They said to themselves, yep, maybe we can solve the Euler equations for practical configurations after all. So I won't really be making very much more use of this diagram because things don't progress in a linear manner after this. All sorts of things start happening simultaneously. So we know some of the fundamentals by now. We're trying to get the answers faster. We need to visualize the results. And we'd like to automate generating the mesh. Generating the mesh was beginning to be a bit of a bottleneck. A lot of the credit for speeding it up goes to another mathematician, this time an Israeli guy called Archie Brandt. And he asked a very interesting question. He said, what is the shortest time in which you can imagine solving a problem? Well, think of the time that it would take you to check that it was correct. You really can't solve it in any time less than that. Could you solve it in a time that is comparable to that? That is proportional to it by some reasonably small constant, like 10. And that was what he set himself to do. I think the idea is probably best presented pictorially. So his idea was to take the grid on which you were going to compute the solutions, shown a very simple grid to make it easy to follow. But the small cells are going to get themselves amalgamated into big cells. The bigger cells are going to get themselves amalgamated into giant cells. And each level of the process has a different job to do. The coarse cells are capable of solving this problem very fast. But if you let them do that, they won't come up with a very accurate solution. So they have to be directed from below. The solution, in a way, is generated by the coarse grid, but checked by the fine grid. And you have to come up with a system of communication going up and down. I like to make an analogy with a perfect democracy, that the object is to make the people happy. The people live down here. When the people are not happy, they vote, and they vote maybe to township level, and then a message goes up to the county, and a message goes up to the state, and a message goes up to the federal government, and then recommendations come down. The thing about this is the recommendations always make people happier, and that's where the difference lies. But geometry, as I said, got to be a challenge. As computers got more powerful, we were able to tackle more complicated geometry. And so a multi-element airfoil, very, very difficult to fit one single mesh around that. And there were really two strategies. One was to break the domain up into blocks, or zones, zone 1, zone 2, zone 3. Within each zone, you have a regular mesh, but the zones themselves need not fit together in a regular way. There could be 3 zones meeting at a corner, for instance. The whole thing gets to be a bit of a nightmare in 3 dimensions. This was successful. It still required a lot of human intervention. A lot of this work had to be done by hand. And it took months sometimes to produce a grid around a 3-dimensional airfoil. If instead you use triangles can be fitted together in many more ways than quadrilaterals can. And that process can be automated. You want to avoid having badly shaped triangles, but other than that, you've got a great deal of freedom. And it proved possible to automate this. It never proved possible to automate the multi-block approach. In fact, recently when the Challenger disaster happened, NASA more or less shut down for a month because Congress was demanding explanations. And the explanations that NASA was trying to provide involved doing a lot of computations. And those computations were all done on unstructured grids because it was going to take too long to generate the grids for the structured codes to work. So CFD under pressure always goes to unstructured grids. Output. What we used to have were things called teletype machines, noisy, clunky, kind of electric typewriters. And what you got was a sheet of printed numbers. And sometimes those sheets of printed numbers went on and on and on. You folded them into a big stack. Maybe you had paper tape. At about this time, I remember trying to make a case to my bosses that what we needed was a color monitor to visualize the results. And we were told we were being frivolous. All the information we really wanted was on that piece of paper, and you just go in there and read it. But it did get to be, slow visualization got to be quite an art in itself. One thing that struck me at the time as being very clever was once you've got the results, you can plot anything you like. So experimentally, you would visualize this flow with Schlieren apparatus. You have a beam of light that goes across the tunnel, gets deflected by density gradients. There's a pattern in which you can recognize things. So you can compute what would a Schlieren system do to the solution that I have computed, and you can look at it in exactly the same way as you would have looked at the experiment. Nice, but it's not full marks. In the future, we'll probably be visualizing results in 3D. There is a startup company in India with the name Virtual Reality CFD, and this is taken from their brochure. And here we have people who are looking at some 3-dimensional image of a simulation. They can walk around it. There's talk even of providing a helmet in which you can walk through it in a virtual world. But meshes were getting still very, very awkward. It was obvious that you ought to make the mesh small in regions where a lot was happening. But that was okay. If you had something like the trailing edge of an airfoil, you knew there'd be a lot happening there, so you could make the mesh small. If something like a shockwave was going to arise in the middle, you had no idea to begin with where that would be. So how are you going to make the mesh around a shockwave small, unless with massive overkill? So the idea was the mesh would adapt itself. And the measure proposed was, well, the error should be the same everywhere. If it's smaller in some place than in others, then that area is using too many resources. But how do you know what the error is, unless you've already got a better solution? So you have things that stand in proxy for the error, like large differences in pressure. Here is a calculation made with an adaptive grid, and you can see the density of points that are packed around the shockwave in order to resolve it. So so what I just said really follows from the expression of the error, that wherever the derivatives are large, you should make the size small, but you don't know exactly where those derivatives are large, so you don't make a guess. Well, that worked. It was a big improvement on what had gone before, but it still had problems. This is not CFD of the flow past some exotic insect. There is actually a NACA 12 airfoil in there right in the middle if you look very carefully. And this is the flow at a Mach number of 0.95, which extends, as I said before, a long way to the side and to the back. And there is a shock wave behind the airfoil like this, which is called a fishtail shock. And when you say that you want an accurate solution to this, the code says to itself, I can see where all the errors are. I better run over there and add a lot more points. Well, actually there are a lot of errors over here that are not actually important errors. They're actually behind the airfoil. This flow is supersonic. What's going on over here cannot influence what is back at the airfoil. So you come with the idea of an important error. This is what happens. You pack lots and lots of points, lots and lots of cells into that region. As you refine the mesh, you add to the number of nodes. That process storms. It gives a value of drag apparently converged, but at the wrong level. It's putting all its effort into improving the grid rather than into improving the solution. And so you need to do better than that. And then you start to say, well, this is an error. Why is it an error? Why am I worried by it? What's it spoiling? So why were you doing that calculation? What did you want to find out? And mathematically, you make this formula and say there's some output, which could be the drag, whatever it is, we'll call it J. And we'd like to know, if I make an error here in this quantity, how will that affect J? And but we know these errors are not, they're not random. They must still, in some sense, solve the discrete form of the governing equation. They're going to come out of our code. Using that, we can define things that we call sensitivities. They're the response of J to an error in density, the response of J to an error in momentum, the response of J to an NJ error. And these derivatives can be thought of as a new set of variables. They actually obey a set of partial differential equations. It is the transpose of the Euler equations. Once we've solved those equations, we then can calculate, because we know the sensitivities, how much an error at this place will affect the thing that we're actually interested in. And by a huge coincidence, Professor Witkowski was actually preparing a lecture on this just yesterday, showing the difference between a mesh that has been adapted by just looking at your intuitive guess of the error and refining the mesh in those places where the error is large. But the drag coefficient converges with a number of elements and it hangs up at the wrong level. It's wrong by 0.001. And if the mesh is refined by only looking at the important errors, all that detailed treatment of the shock wave just goes away. The code actually is smart enough to know that it needn't worry about errors in that region of the flow. And the answer that the code converges to is then correct. One thing that is a trend is that always strikes me that you can write the fluid flow equations in a great number of different forms. Start with the conservation laws, play with them, you get characteristic form and laws concerned vorticity and entropy. We don't know how to incorporate those additional forms very well. And so what is happening is that more and more emphasis is being given to what you might call secondary quantities. We learn to work those into the calculation. If you say the only thing I'm really interested in my solution is the balance between the entropy out minus the entropy in plus the entropy created, and optimize to get the best possible balance of the entropy, you actually get very nice grids. And in this case, you know what the answer should be. It should be 0. So not only do you know where you've made the error, you know exactly how big of an error you've made. And that gives very solid guidance about what the errors are in the other quantities. And so we're getting to have CFD with error bars on it. And that's a very important development. I want to mention this. If we have the flow past a circular cylinder at hypersonic speed, there should be a nice, smooth, detached bow shock ahead of it. CFD codes very often give this alternative solution. You think this is just a mistake, but it's hard to find any way in which this does not satisfy the order equations. And it is even the basis for an aerodynamic device. There's been a device around for a long time called the Aerospike, which you put onto the nose of a blunt body in order to modify the flow pattern in very much that way. You get an oblique shock, and you get reversed flow behind it. And this reduces drag, it reduces heat transfer. It's not all that reliable when you put it at incidence, which is the big snag. In this case, you have to do something to the flow before it modifies itself. In this case, you don't have to do anything. It decides to modify itself. How are you going to tell the code that this is wrong? It's a very difficult question. Lots and lots of solutions have been proposed. I'm not convinced by any of them. Okay, this is going to be a master thing. What does turbulence look like? Calculations of turbulence. So the obligatory Leonardo da Vinci sketch of turbulence. And then experimental visualization of transition. This just looks like a big mess. This looks pretty much like a big mess as well. That's what our idea of turbulence has always been. It's a big mess. So in Japan, they have a very big computer called the Earth Simulator because they're interested in earthquakes and tsunamis and things like that. A huge computer devoted to those things. And they compute turbulence in a box, so a square box containing 5,984 cells in every direction, so 10 to the 11 cells in all. This is a few years ago. These are small numbers by today's standards. But I don't think this calculation has ever been done better. Inside that box, you solve the incompressible Navier-Stokes equations because at a small scale, everything satisfies the laminar Navier-Stokes equations. And you look at it. And what you're doing is you're taking a slice out of the box and then doing a three-dimensional visualization of what you would see. And well, certainly it looks like a big mess, but you can see there's a lot of structure to it. There's a lot of filaments. And when you zoom in on the enclosed area, you see pretty much the same again. Zoom in again. Zoom in again. If you ever want to know what a can of worms looks like, this is probably it. Interesting question, what are you looking at? You're looking at surfaces of constant something, probably. Well, a bit of insight. Vorticity, rotation, cannot be created according to the Navier-Stokes equations except at a wall. So everything that is rotating in this image was at one time adjacent to a wall. That doesn't quantify much of the fluid, so the percentage of fluid that has rotation remains constant and very small until a very late stage in the day. And so you look at the simplest analytical model of a vortex. The circumferential velocity inside something called the core varies linearly with radius, that is solid body rotation. After that, it falls off in the potential vortex that everybody learns about in 325. The vorticity is constant in this region, and it falls off very quickly like 1 over r squared. We'd like to pick up these regions. We'd really like to pick up these boundaries, if we could. The way those plots were done was to connect up all those places where vorticity is above the local average by 4 standard deviations. What experiment could possibly allow you to visualize those surfaces? What other criterion could you possibly give to an experiment that would give you an equally vivid picture? So that's the reason why I say that CFD is very much more than an experiment. And I did really prepare more material than I needed, but I think I'm going to stop there. But where are we going? Current NASA study, looking forward to, well, CFD is okay for predicting steady flows in a design condition. It's not okay for predicting unsteady flows with turbulent separation. Could this be remedied by 2030? Advances in hardware alone over the next 20 years, just Moore's law by itself, will not be sufficient to achieve these goals. Several orders of magnitude improvement in simulation capability must be sought from advances in numerical algorithms. And one conclusion I draw from that is the people who are studying CFD, fundamental CFD today, are not actually going to be out of a job for the next 20 years. Skip that. What is behind the curtain? I've tried to introduce you to the wizard. You've realized by now maybe that some of his magic is a bit bogus, but I think you've also realized by now that some of his magic is perfectly genuine, and you can in fact trust it. Knowing what to trust and not what to trust, not what not to trust, means you begin to understand what CFD is about. So thank you.